Okay, here we go. Let's take a look. We want to look at hydrogenation of lipids. We already have seen in an earlier video hydrogenation of fatty acids. It'll be the same thing for hydrogenation of triacylglycerols. Hydrogenation is what it has been ever since we learned alkenes. Hydrogenation is this. Carbon-carbon double bond plus hydrogen, right? Hydrogenation, hydrogen. Carbon-carbon double bond plus H2, some sort of catalyst, maybe nickel. The double bond breaks, and each carbon gets an H. So double bond turns into single bond, each carbon gets an H. If you try to do this with the alkane, a saturated hydrocarbon or saturated lipid, you'll get no reaction. You'll have no reaction because there's not a double bond. So this is why I said hydrogenation of unsaturated lipids. Saturated lipids are this. They cannot undergo hydrogenation. Let's look at then an unsaturated lipid. This one right here is unsaturated. It's polyunsaturated. I can see a bunch of double bonds. 1, 2, 3, 4, 5, 6, 7, 8, 9. There's 9 double bonds. And if I'm going to hydrogenate all of them, then I need 9 hydrogens, 9 H2 molecules. I need an H for there and an H for there. That's one H2. I need another H, that's a second H2, and so on. There are 9 carbon-carbon double bonds, so I need 9 H2s. That's to make complete hydrogenation, doing that to all the double bonds. When I do that, check out what we get. There it is. All the double bonds are gone. The number of carbons does not change. The ester bonds don't change, but look, carbon-carbon single bonds everywhere. I turned a poly unsaturated triacylglycerol into a saturated triacylglycerol. And if you make a connection between this and what we learned a little earlier, this will have a lower melting point. This will have a higher melting point. Saturated fats tend to have a higher melting point. Make sure you can see that. Lower melting point here, higher melting point here, because the carbon-carbon double bonds are gone. So, if you do this, and now let's connect it to food, if you take something like olive oil or soybean oil that's unsaturated, polyunsaturated, and you react with hydrogen, enough hydrogen to turn all of the double bonds into single bonds, you'll end up with a saturated triacylglycerol. What happens though is the melting point gets so high when you do that, instead of soybean oil, it'll be a solid, and it'll be a pretty firm solid. This would be about like frozen butter maybe. The melting point is very high. When food companies wanted to make margarine, for example, by hydrogenating corn oil, they discovered if they used as much H2 as they thought they needed, they got something like frozen margarine. So they said, let's try something different. Let's try this. Same molecule as what we just saw. It's polyunsaturated. This is a polyunsaturated triacylglycerol. Triacylglycerol has a lower melting point because of all those carbon-carbon double bonds. If we react with just not quite as much hydrogen, we have 9 carbon-carbon double bonds, and we won't give it as much hydrogen as that. We'll give it 3 hydrogens instead of 9. So this is called partial hydrogenation. Only some of those carbon-carbon double bonds can be hydrogenated because we're not giving it enough hydrogen. Look what happens. In some of the molecules, we see that a few of the double bonds have turned to single bonds. That's exactly what we expected. That's hydrogenation. These 2 double bonds right here are gone. They got turned to single bonds. That's what we expected. The melting point will be a little bit higher. Won't be all the way high because we still have some double bonds. This is what the hope was, to do this. Make a slightly higher melting point. Some of the double bonds as we see here, don't change at all. So this is just another example here. I'm pointing out that some of the double bonds turned to single bonds, some of them did not. This will be a little bit higher melting point. But an unexpected result was this. This example here, some of the double bonds have done this. This one here, this one here. These have turned to trans. You can see that it's trans. I've highlighted that trans bond. That's going up, this is going down. That's opposite, that's trans. Up on that end, down on this end, that's trans. Compared to this, where it's going up and up. This is a cis bond, this is a cis bond. That one's trans, this one is trans. How about this top one? That one looks like trans also. That's trans. Also, what we saw when we were looking at fatty acids is that trans fatty acids, aside from having a higher melting point than cis, we have learned that trans fatty acids are very unhealthy for you. So I said, notice, when you partially hydrogenate an unsaturated, some of those carbon-carbon double bonds, which naturally are cis, some of them switch to trans. And trans is very unhealthy. So when you partially hydrogenate, you'll get trans. Make sure you see that if you completely hydrogenate, like we just saw, complete hydrogenation does not give trans. There's not cis or trans, right? You got rid of all the double bonds. No carbon-carbon double bond, then no cis, no trans. But if you partially hydrogenate, so there's still some double bonds remaining, some of those flip to trans. Partial hydrogenation is no good because it produces trans. You cannot hydrogenate a saturated fat. Whether it's partial hydrogenation, complete hydrogenation, that doesn't matter. Remember how we started. We said if it's saturated, no reaction with hydrogen. Only unsaturated can react. So both fatty acids and fats can be hydrogenated as long as there's a carbon-carbon double bond. That's the only part that matters. It doesn't matter if this is part of a fatty acid or part of a triacylglycerol. If you see carbon-carbon double bond, yes, you can hydrogenate it, either completely or partially. If you see that all the carbon bonds are single bonds, whether it's a fatty acid that's saturated or a triacylglycerol that's saturated, you cannot hydrogenate it. Partial or complete, doesn't matter. You cannot do it. If it's all carbon-carbon single bonds, you'll have no reaction.